So thanks for having us today here. We are, I'm the former global CTO of AI at the Linux Foundation. I previously led the PyTorch Foundation as the executive director and CTO, and I'm a visiting scholar at Columbia University. So before we begin, I would like to share some thoughts as we are living through unprecedented times. AI capabilities are advancing at a pace that would have sounded implausible only a few years ago. Models can reason across long contexts, write and execute code, use tools, and operate software, and coordinate increasingly complex workflows. We are entering a world where powerful models can solve complex mathematical proofs, generate extensive code bases, and power systems that take actions in production networks that have real-world impact. But exactly at this moment, when AI is becoming more capable and more consequential, openness is under genuine pressure. So the idea of restricting or even banning access to open weight models is no longer a hypothetical, right? It's being actively debated in Washington and elsewhere, and we're also hearing proposals that to attempt to control the frontier through chips, compute, distillation, safety testing, and model release processes. The safety and security and national security concerns behind these discussions are real and legitimate. They deserve serious, technically informed responses. But we must also be equally clear about the risks on the other side. Blunt restrictions can concentrate capability, infrastructure, and decision-making to a very small number of institutions. They can transform artificial intelligence from broadly accessible and general-purpose technology into something that the rest of society is only permitted to rent from a few labs. That cannot be the foundation on which we build the future. Openness is how we create competition. It is how researchers inspect systems, developers adapt them, students learn, enterprises maintain sovereignty over their data and stack, and countries build AI capabilities without being permanently dependent on a single vendor. So openness is also an essential part of safety. It enables reproducible evaluation, transparent interfaces, independent scrutiny, shared security tooling, and the ability to identify and correct problems. Sorry. Oh, there's no slides. It's just me rambling. But open communities allow more people to test assumptions, discover vulnerabilities, compare approaches, and contribute to solutions. But openness does not mean ungoverned. It does not mean being careless, unsafe, or a free-for-all. Openness means that systems can be inspected, evaluated, adapted, and improved. It means that interfaces are interoperable, implementations are contestable, and no single organization controls every layer or decides who's permitted to participate. This becomes even more important as we move into agentic AI, because an agent is not simply a model. An agent is a stack. It includes the model, the harness, the tools it can invoke, the environment in which it acts, guardrails, the reinforcement learning systems through which it improves, the evaluation infrastructure that measures it, and the compute on which the entire systems rely. An agent may depend on APIs, credentials, sandboxes, memory, inference systems, orchestration frameworks, and multiple forms of specialized hardware. It may cross organizational, cloud, and geographic boundaries while completing a single task. If any one of these layers becomes closed and vertically controlled, the entire ecosystem becomes less portable, less competitive, and more fragile. That is why open models alone are not enough. We also need open environments so that agentic tasks can be reproduced and shared. We need open reinforcement learning frameworks so that more people can improve models and agents. We need open compute layers so workloads are not captive to one cloud or compute vendor. And we need open standards so all of these components can work together without requiring permission from a central platform. The open agentic stack is therefore not one project. It's not one framework or one model. It is a shared architecture built from open source software, open standards, and composable components. And that is the arc of today's workshop. We will examine 4 foundational layers of that stack: environments, models, reinforcement learning, and compute. Each talk addresses a different technical challenge, but they share a common principle. The future of AI should be modular rather than monolithic, interoperable rather than captive, and open to participation rather than controlled by permission. This is not simply a philosophical reference. It is an architectural, economic, and strategic requirement for a healthy AI ecosystem. So thank you for being here, and thank you for contributing to that future. With that, we will begin with our first speaker, Ben Burtonshaw. So Ben is from Hugging Face. Ben will introduce OpenEnv, an open standard and community hub for building, sharing, and running agentic environments. These environments define the tools, APIs, credentials, execution contexts, and tasks through which agents learn and operate. Ben will explain why shared environment specifications and harness protocols are essential for reproducible training, safer execution, and collaboration across the open source ecosystem. So with that, please welcome Ben to the stage.
Hi everyone, so as you heard, I'm Ben from Hugging Face, and I'm going to talk to you about a project called OpenEnv and open source Agentic RL environments in general. My opinion, my hypothesis, is that RL environments are the best way to democratize AI, the best way to kind of take a stake in AI, mainly because they're pretty easy to build. They're just applications, they're just the kind of things that we do on a daily basis for that reason, and everyone can get involved. So I'll work through this in a pretty kind of high level and ecosystem kind of perspective, and then Daniel's going to kind of go even deeper on RL, and we're going to go quite far on it. But if I miss anything, please come and ask me questions afterwards or contact me. So what is an RL environment, right? The simplest way to explain what an RL environment is that it's a world that an actor acts within, or that an agent acts within. The kind of original RL environment would be a chess game, where the board is the world, the pieces are the state of the environment, the rules are the actions or the moves that you can make within the game, and the score, the game score, is the reward. And in reinforcement learning, we would use that reward to update our agent and to learn from that. So that's just a game, but let's kind of scale that up now to something a bit more realistic. So we could take software engineering. If we say that software engineering is defined as a task that's in a GitHub issue, and the work is in the GitHub pull request, and the score of that work are the results of the test suite and maybe the CI, then we would say that we have an environment that's there for software engineering. And this is how papers like Smith and others have built software engineering environments. We could take this and we could then remove the work that from the pull request. We could remove the code from the pull request and get an agent to generate that code in that same environment and use that test suite to get our reward. And then we have an environment for a software engineering that we could use to train a software engineering agent. Now, we could carry that archetype across many different tasks, right? Email triage or, say, project management. And we would need to find the tasks, the reward, and the state within those environments and build them into applications. And so this is what we're talking about with RL environments. OK, so what does the ecosystem look like? So to explain this, I kind of like to go back to something called the matter cycle. If you studied machine learning at school, you would have encountered it. It's the model, annotate, train, test, evaluate, revise loop. And it's not so common nowadays because it's a little bit outdated for modern machine learning, and we kind of need to update it a bit. So I like to update it to what I call a capability cycle. So if we look at a capability cycle, we would say that we discover capabilities, we then benchmark them, we represent them in data, and then we train models on them. Typically, we discover a capability with a harness or with some kind of prompt, right? We elicit this capability out of a model, and we can see that, OK, it is able to do a certain thing, maybe not reliably. We can then evaluate that capability, and we'll typically use another software stack for that, and we'll have an evaluation harness that will measure this capability in the model and how frequent, how reliable it is. And we can iterate upon that as a community. Next, we'll want to represent that as, firstly as a data set and then eventually as an environment. And that's where domain expertise will come into this. And so companies like Mercor will do a great job of building reinforcement learning environments around capabilities for which they'll go out and speak to and hire domain experts in the respective domain and build that environment that encapsulates that capability, partially based on the benchmark, but ideally without any form of leakage between the two. And we'll then have a means that we can train a model on. And so that's when the trainers will come in, another part of the software stack, but also another community. Right now we'll have labs that are training models using these data sets and environments. So what you can see from this kind of capability cycle is that environments are the kind of the means with which that we move capabilities from domain experts into the models that we use. And once the models and harnesses have these abilities, then we kind of move on to the next one, and we know that, right, this capability is in the weights, as it were, right? Okay, so that's a really high-level view. What you'll take from that cycle is that there are many moving parts, many different communities all playing in on the environment, and therefore it's a really important part of the stack to be open, right? This is the means with which that we're communicating capabilities. Like imagine if data sets were in a closed format. It would kind of be it would be a particularly horrible situation. And that's the goal of OpenEnv. So if you look for environments, you'll typically go to papers and GitHub, and you'll find that they're very distributed. If you look at the recent Kimi K3 paper, it came with thousands of environments. The Minimax paper had, I think, 10,000 environments. Even the first DeepSeek paper had roughly 1,000 environments. And all of these are implemented in different ways. Some of them are shared in different ways. Many of them are sold. And they're not something that's readily available in the way that open weight models are. It reminds me a lot of kind of being an MLE back in, say, 2017, when you would find weights, you would find implementations for models on GitHub, and then you'd go to Google Drive and you'd find the weights from there. And nothing is really exposed and interoperable in the way that it is today with model checkpoints. So that's the problem. And then that problem kind of compounds when you start to look at training. Daniel's going to go into this in more detail, but at a high level, a training process is a framework, right? We have a library like TRL or Unsloth that we use to update our model based on some kind of action that it does. And in this environment, we want to use, in this context, we want to use an agent harness to perform the task. So let's say it's the software engineering task. That agent harness is going to do that and interact with this environment, use tools in that environment, and then we're going to update the model. So at each of these edges, we have a different layer that needs to be interfaced, right? And we can't have a harness that expects a certain environment definition, and we need to also work with multiple harnesses like Pi and Codex and Claw Code, etc. So the challenge kind of compounds. One of the main mechanisms that we're working on in OpenEnv to get this to work are environment hubs. So on Hugging Face, we have about 4,000 environments now that can be pulled in a standard format that you can plug into most major training frameworks. There are other environment hubs like Prime Intellect, and there are also more coming, and we're collaborating with orgs to share our specs so that if they build environment hubs, they'll be able to use a spec such that they can download environments and share them in an easy way. So in code terms, like this is what it looks like to use OpenEnv. We imagine that it would mainly be driven by an agent, but it's a bit like Docker. So you'd say OpenEnv init, and you would get a scaffold of a kind of hello world environment that just gives you a generic score. And from that, you would just need to write the business logic for your environment, or you could generate the business logic with a code agent. You could also import environments from different libraries like verifiers, and then you can push, pull, and fork environments on the hub so that you can share them or use other people's and adapt them. That's the base layer of OpenEnv, and the features that we're working on next are to be able to discover environments from hubs and then to be able to validate them. So at the moment, the process of finding an environment for your use case is quite difficult. But if you could search for environments on the hub, you'd be able to pull those and get a range of community environments, which is quite nice. We can share with each other. And then that creates another challenge. How do I know which environment is better? How do I know which environment is going to help on my use case? And that's where this new validate command comes in, where we'll say, okay, this is a valid spec, and also we can train a small model to see if it lifts performance on a given benchmark. So with these two commands, we'll have an autonomous loop for integrating environments in post-training. Okay, so the last block of the talk is then how can I use an RL environment? So the quickest way to get started would be in evaluation, and I'd suggest that kind of most people do this because you can represent a typical workload as an environment and you can see how good a model is. So you could take a model as weights or as just an API, and you could define your environment with a set of tasks and a reward function and run the model over those tasks, and you'd get back an aggregate score of how good a model is at your environment, right? The main way, or the core way that we would look at this would be with reinforcement learning. So we would take a model or a policy, and we would roll it out over this environment and get a set of actions. And then we would calculate rewards on each of those rollouts. We could use an algorithm like GRPO, which Daniel I know is going to come into further, where we would calculate the reward for each of those rollouts and then take a mean across the whole group and update the weights based on that mean. And then we'd iterate like that. So if you're interested in more detail on this, I've got a few talks where I go into greater detail on this, but at a high level, this is how we'd use an RL environment. And then the next way would be distillation. So in this setting, you wouldn't really be able to distill from strings, like you wouldn't be able to distill from tokens. You would need log probabilities. And we would take a student and a teacher model. We would roll out the student, so we'd get it to perform a task inside an environment, and we take the log probabilities of that student on this task. And then we would get a teacher to do the same task, or to roll out over the same token, and we take the log probabilities of the teacher on those tokens, and then update the weights of the student based on the difference, the reverse KL from the student and the teacher. That's one way. We could do this in a few different ways. So we could also take the student and do self-distillation, where we say, okay, let's take the best example of the student and compare it to the average. Or we could give the student some kind of privileged information or hint. We might get that from the environment or from a data set. Like, for example, in the pull request setup, we could say, here's the actual solution to this code, and we give that to the agent at the beginning, and then we update the weights based on the difference between its bad run and its good run. Okay, so that's the core of OpenEnv. That's what we're working on. The main takeaway is that we're trying to make it so that open environments can be shared openly across the Hugging Face hub, but also others. And how do we think that this is going to work? How do we think it's going to be effective? The answer to that is leaderboards. Like we kind of see environments at the moment existing in a bit of a shadow realm. Like they're not really spoken about that much, or they're not really seen within the community around model releases. And we think that if people can start to build their own environments and try them out, and then we put them into leaderboards and we figure out which ones are good and which ones are contributing to model success, then more people will get involved and we'll share more of these leaderboards. So that's the talk.
Thanks, Ben. Thanks. Thanks. Hello. Thanks, Ben. Hello, is this working? All right, so there, it's actually working now, okay. So our next speaker is Daniel Han Chen, co-founder of Unsloth AI. Daniel's talk has a wonderful direct title, Making Open Models Not Suck. Open models are advancing rapidly, but anyone who's deployed them in an agentic system has encountered some practical problems for sure. Looping behavior, malformed tool calls, unreliable formatting, and failures that compound over long-running tasks. So Daniel will examine why these problems occur and what developers can do to make models more reliable, efficient, and genuinely competitive with closed systems. So with that, please welcome Daniel to the stage.
Hello. Hello? Oh, yes. Okay. Hello, everyone. Thanks for coming today. Yes, we have... Oh, wait. Okay, wait. Let me check. Oh, okay, there we go. Okay. It's a bit awkward, the computer, but okay, let's see if it works. If the slides, fail, please tell me. But yeah, hello, everyone. I'm Daniel from Unsolve, and great to be here. But today I'm going to be talking about how to make open models not fail, not suck, and how to make it much better overall. Yeah. So for you folks who don't know us, we're Unsolve. We are one of the largest organizations on Hugging Face, and we distribute models to the entire world. Okay, that number is outdated, but we have around 400 million total downloads on Hugging Face. We distribute the largest models and the smallest models, and we're the third largest distributor in the entire world. We also don't just distribute models, so we also fix bugs and open source models. So we collaborate with all the large labs and hardware providers in the entire world to fix issues in the models before you get them. So if you're using open source models on your laptop, on your computers, they're most likely fixed by us in some way. For example, OpenAI's GPT-OSS had some issues. Llama, Gemma, Mistral, all of these models have some issues. And we're here to help make the models much better for people to use. Recently, most people should know, Kimi K3 has been launched. It's the world's best open weight model that anyone can download. So they just released, you can download this on Hugging Face. It's quite large, 1.5 terabytes, but you can download this on Hugging Face. It was just released just a few days ago, Monday. And for what we did is we quantized it down to 1 bit for you to use. So it's not 1.5 terabytes anymore. It's around 600 GB. And Kimi K3 was actually 4-bit. So it's actually not that easy to quantize anymore because 4-bit going to 1-bit is not that much savings. But we show that you can retain 76 to 78% of accuracy, but you can reduce the size by 82%. So it doesn't, when you reduce the size of a model via quantization, you're not going to make the model 82% dumber. It's only 16 or something % dumber. And we show, for example, some examples. A 1-bit Kimi did pretty well on some prompts. This is 1-bit, okay, versus the Kimi K3 at 4-bit, so the full precision, versus Claude, Opus, and GPT. DeepSeek just released an update yesterday. Was it yesterday? Yeah, I think it was yesterday. But yesterday they released 0731 for DeepSeek V4 Flash. So that was an interesting release at a weird time, and then they just randomly dropped it at some weird time zone. And so we also quantized it down for people to use. So you only need to use 90 GB of VRAM or RAM for you to run DeepSeek V4 Flash. And it is, I would say it's the best model for its size. So Kimi K3 is still much better, but it's ginormous. But DeepSeek V4 Flash can actually fit on your local computer and run it. So it works very, very well. So as open source models and closed source models, both of them are getting better and better over time. For folks, I'm not sure if you have seen the meter plot. So the meter plot shows the meter plot shows how much progress is there in AI. So for example, you can see Claude. The plot is a bit outdated because they have not updated it. But models can do tasks that take humans 16 hours to do, and it can do this very, very well. This is a 50% probability. So the 80% probability is a bit less. I think it's 6 hours or so. But you can see models are progressing at an exponential speed. If you log it, so if you do a linear trend, you can see that the exponential progress is much more clear. I also plotted Mythos or Fable as the red line, and also GPT 5.6 Sol. So this actually removes cheating. So some of these models, they like to cheat. If you do include the cheating examples, then GPT 5.6 Sol is 270 hours. So if a human can do a task that takes 270 hours, GPT 5.6 Sol can also do it. However, that's probably not a good example. So if you remove all these cheating examples, it's around 16-ish hours. But you can see over time that models are improving at a dramatic pace. If you squint a little bit, there is actually this horizontal line area, right? So if you can see around 2023 to 2024-ish, there is actually a plateau approximately, if you can squint a little, right? So GPT-4 to GPT-4o there was not that much progress. And the main reasoning behind this is because reinforcement learning and reasoning was not invented during that time. And so if you plot two different plots, like line plots, a trend, if you just plot the non-reasoning time frame versus the reasoning time frame, you can see that if we did not invent reasoning, so if O1 preview, if OpenAI did not tell everyone you can do reasoning, then AI models would have plateaued. And so if you can see the gray line, if you just plot, if you just fit a trend to the models before the reasoning age, all models would have plateaued by now. And the doubling time, so every single 7 months, the models will get double in capability. That was the olden days. But now the green trend is when you add reinforcement learning, you add reasoning, and you can see the doubling time has shrunk to 3.5 months. So this means you only need to wait 3.5 months for the model to be double in capability. So Opus 5 just got released a few days ago. Wait 3.5 months, and you'll get an even better model than Opus 5. But remember, the trick is if the trend continues, right? So that's the fundamental question. Will the green line continue and continuously keep increasing for AI capability? Or we will go back in time and go to the gray line again, right? Will AI just slow down and slow, and then we have to reinvent something new again? So this is a question that we will see in our lifetimes. So all you need to do is wait a few months, and we shall see, right? So if you see models are plateauing, then this means AI has plateaued. So all you need to do is wait 3.5 months to 7 months, and we shall see the trend. So there is another very cool plot by artificial analysis. So they show open models versus closed source models. And you can see the blue line is open source models, and the black line is closed source models. And if you see very closely, open models have very, very closely reached closed source models. A better indication, I'm not, my favorite gauge, if you want to look at one benchmark, don't just look at SweBench or DeepSwe or whatever your favorite benchmark is. My favorite one is actually WeirdML. So if you search in Google WeirdML, this one is my favorite benchmark. And the reason why it's actually very hard to game. And you can see the blue line is open models, and the green line is closed models. According to WeirdML, Fable 5 is pretty good. It's very expensive, so I would suggest you to use Opus 5 High, which is, according to WeirdML, the best for its cost and accuracy. But for open models, Kimi K3 is extremely powerful. You can see, for example, they also plot the accuracy across models. So Fable 5, okay, that has the highest accuracy and max reasoning, but it is very expensive. It's ginormously expensive. The next one is Opus 5 Max, Opus 5 High, and so on. And you can see Kimi K3 is also on the leaderboard. So open models are definitely catching up. In fact, if you squint a little bit at the plot, this is a bit delayed. If you squint a little bit at the plot, there is actually the delay, as I was talking about, O1 preview and open models. And so this delay is what we call the open source drought, which was around 1.5 years ago. And in fact, if you take the closed source models minus the open models, you have this trend, which is the progress of open models. They're closing the gap. This line is a bit outdated, so it's more like 2 months delay. But you can see that with the invention of reinforcement learning and DeepSeek publishing how to do GRPO with DeepSeek R1, open models then again went back to trend. And so in fact, if DeepSeek R1 did not publish GRPO, open models would be 16 months behind closed source models. But now it's only 2 months behind. And there is this good blog post showing a trend extrapolation. By 2026 December, so in a few months, we shall get an open model that is as good as a closed source model. But this is all trends. So who knows if this is going to happen? All we need to do is wait a few months, and we shall see. And so we shall see if open models can, in fact, be as good as a closed source model by December 2026. Another trend, I don't know if you guys saw, OpenAI decreased prices of GPT Luna by 80%. A few days ago. This might sound very shocking, but actually it is not. And you can see on the DeepSwe, I don't know if folks use the DeepSwe benchmarks, but the DeepSwe benchmark shows that GPT 5.6 Luna is extremely, extremely efficient, cheap, and also very smart. And so the DeepSwe plot is to the right, to the top is the best. And so you can see GPT 5.6 Luna has dramatically shifted the line. And so the main question is, token prices are plummeting, but is this reasonable? People are thinking, okay, maybe OpenAI is just shedding all their money. Why can DeepSeek charge 10 cents versus other providers charging $1, right? Is this actually correct? So actually, I did a calculation over before the talk. And so I don't know if you folks know semi-analysis. They released something called Inference X and benchmarks for VLLM, SGLang, and other inference engines on NVIDIA GPUs and AMD GPUs. And according to their benchmark, DeepSeek V4 Pro, so the biggest one, on one GPU, one B300, GB300, you can do 13K tokens throughput. If you calculate this, that means 1 hour you get 47 million tokens. If you saturate the GPU, 47 million tokens. Then if you look at the price of GB300, it's around $5 per hour, approximately, per GPU, according to a semi-analysis, right? $5 approximately. And if you calculate this, right, you can do 47 million tokens per hour, $5 divided by that. That means that DeepSeek V4 Pro, the minimum floor price is 11 cents per 1 million tokens. And what does DeepSeek charge? DeepSeek charges 44 cents per 1 million tokens and 87 cents per 1 million tokens output. So this means that if you run DeepSeek V4, approximately, it's not a loss, right? It's not like OpenAI is shedding money or like DeepSeek is shedding money in terms of running these models. And that is why OpenAI can reduce the price of GPT 5.6 Luna to 20 cents and $1.20. And why? Assuming GPT 5.6 Luna is the same size as DeepSeek V4, okay, it's most likely not, but it's assuming it's the same size, then OpenAI still raises some money, around $1 per 1 million output. If you extract, also Kimi K3. So Kimi K3 is a new architecture. It's still not very optimized, but if you look at semi-analysis analysis, Kimi K3 takes around 5K tokens throughput per GPU. So it's around 2.6 times less than DeepSeek. And if according to Kimi K3, I don't know if you guys use the model, it is $15 per 1 million output. That is extremely expensive. And why? Because if you divide it, so it's actually 29 cents. The floor price for Kimi K3 is 30 cents per 1 million tokens. So Kimi K3 so Kimi, Moonshot, and the other inference providers are getting $14.70 on your API cost. So if they wanted to reduce price, they can, all the way to 30 cents. Obviously, well, you still need some revenue and some profit. So the price of these models are still slightly inflated, and DeepSeek is the only one which is charging, at close floor prices for their models. Another plot that I really like to look at is Arena. So Arena has this like Pareto efficiency plot. Folks probably looked at Arena's scores and stuff like this. I don't really like the Arena score, but the good way is to look at the Pareto efficiency plot that they publish. And you can see that, so to the top, to the right is always the best, as normal. But you can see there is a lot of models that are in this, Pareto efficiency line. And, for the performance that you want, you should look at which model you want to use. And so many open source models are also on the Pareto efficiency front. For web development, so if you want to do HTML development, web development, and stuff like that, Opus 5 Max for now is the best. However, Kimi K3 is just behind it. So if you want to use like a slightly cheaper model, and if you want to have still very good accuracy, Kimi K3 is a very good model. GLM 5.2 is also on the on the plot, and other models. But if you don't want to pay API costs, there is another way. You can run the models locally on your computer, right? And the cost becomes zero, right? Not any cost, just electricity cost. Okay, some setup cost, some front-loaded cost. But yeah, essentially that is what we do. Essentially, we can reduce a model size to very, very small bits, like 1 bit, by using dynamic quantization. And we show many, many Twitter posts about this. We did it for GLM, we did it for Kimi, we did it for many, many, many other models. So if you go to our Hugging Face page, you can download these models that you can run locally on your computer. Some of them are very big. So Kimi is still 600 GB. So I'm not sure if that can run on your computer. But we're trying our best to reduce it to 1 bit, and even below 1 bit. How can we make Kimi 250 GB, for example? For example, a very good example is GLM 5.2, 1 bit. You can this is one-shotted prompt. So we don't tell it to edit bugs or fix bugs and stuff like that. And you can see that GLM 5.2 does very, very well compared to the other closed source models. And remember, this is 1 bit versus full precision. So this is not like some full precision model. We also show perplexity benchmarks to show you that one bit works well. KL divergence. So another way to benchmark these models is to use KL divergence. And yeah, so, oh wait, how much time do I have left? Or is that? Oh, OK. I shall skip this then. OK, I will skip this. OK, the last thing I'm going to talk about is Arc AGI. So folks, if you know, a few days ago, OpenAI posted that in order to make models good, they showed that the Arc AGI benchmark is actually a bit bad for GPT. And the reason why is because they had a rolling truncation of 175K tokens. And they did not enable compaction. And they did not enable preserved thinking. And if you just enable these two flags, you can make OpenAI's models increase all the way to 40% accuracy. You don't need to do anything. Just enable compaction and do preserved thinking, and you will get high accuracy. And I was going to say other stuff like, oh, whatever. There's not enough time. We have some slides. I'll put some slides off. But yeah, thank you for listening, I guess. Yeah.
Thanks, Daniel. All right, so next up, we have Sheng Yang from Radix Arc introducing Miles, a flexible and scalable reinforcement learning framework for enterprise-facing agent training.
OK, good afternoon, everyone. Thanks for the invitation. My name is Sheng Yang, and I'm a research resident at Radix Arc and a PhD student at MIT. So today, I'm very glad to introduce Miles to you guys on behalf of the team. And to begin with, Miles is a production-facing system for reinforcement learning on frontier language models with very fast speed and stability. And today, we will first give you a very brief overview of the overall architecture of Miles, and then highlight some recent new release and new features of the Miles system. So let's dive in. And first of all, the first question is, what is Miles? And it is an open source RL engine for frontier models developed by Radix Arc. And the key point for Miles is that it's a stable, efficient, and reproducible reinforcement learning system at scale. So you can minimize the effort to run a reinforcement learning job on the modern language models with different kind of environments and different kind of reward designs. So at a high level, there are 3 layers in Miles. First of all, we have SGLang as a reward engine, which is specialized for high throughput multi-turn generation, and it's also very compatible with nowadays agentic system, agentic environments, and agentic infra. And in the middle, we have the orchestration layer, which organizes everything like a reward engine and backend training systems as a whole, so you can make the RL system run very efficiently. And finally, we have support different kind of training engines, such as NVIDIA Maxtron and FSDP. So it's also very flexible, and you can customize your own training engine on your own compute resource. And here are a key picture of the Miles architecture. So on the left, we have reward engine, which generate trajectories by interacting, for example, with the external environment. Or an agent framework, and the SGLang provides a generation layer. So while the environment itself can be very customized or alternated based on the customer's requirements. And in the middle, the system turns the trajectories into some rewards, some loss functions, etc. So you have the training signals. And finally, we have as we mentioned, we have the Maxtron or FSDP as the training backend. So you can update doing the forward and backward and compute the loss and updates of model weights. And finally, these model weights will be synced back to the inference engines, the reward engines, so the whole pipeline can run in the circle. And why we use SGLang as a reward backend, there are just some advantages. First of all, it's co-evolved with the RL workload, so including the partial reward support, and we can have dedicated reward control. So it's very easy to have your workload specified. And second, its router design is very high performance. For example, you can have a very well-designed cache-aware load balancing for high throughput generation. And it also natively supports asynchronous generation with training engine, which is a very important feature in nowadays reinforcement learning algorithms. And it's also fast-moving and and there are a lot of optimizations. For example, SGLang supports speculative decoding with mouse, so you can use speculative decoding during the rollout stage of reinforcement learning. And here are some key points that why mouse can change RL developers workflow. So as we mentioned before, the first thing is that it's customizable. So we can support different kind of workloads just with some customizable function paths. So it can be very easy to define your own IO workloads and your own reward function and some update method. And it's also modularized and non-invasive. So it can be very easy to change to different training backends, for example, as we mentioned, FSDP and Magshon, and we will also support different kind of training backends in the near future. And here are some more technical details about the system design. So first of all, we have the rollout engine, and we support multi-turn agentic rollout, as we mentioned a lot of times before. And specifically, we support token in, token out, TITO for short, which means that we don't need to do the tokenize and detokenize again and again for the same multi-turn generation. So it can save a lot of cost and also makes the training more stable. And we also have R3 for MOE models, which means routing replay. So when training MOE models with RL, so you don't have to worry about the replay kind of things, which means that for different rounds you have different different expert routed for the same request. We don't want that, so we have the R3 to make sure that it's fully reproducible. And on the training side, we also support low precision RL, such as end-to-end MX FP8 support, and we also support per token NVIP4 quantization for the rollout stage, so that it can greatly decrease the training latency and increase the training throughput. And all these kind of things has been verified in our latest blog with the real-world training workloads. And we also have the LoRa support for resource-constrained scenarios, so that you can train large model with a smaller number of GPUs. And here is the current support metrics of the mouse. We recently launched the day zero support for newest models such as Kimi K3, the Inkling from Thinking Machines Lab, and we also support like DeepSeek V4, Nematron Ultra, etc. And we also have a wide range of precisions, as we mentioned, and also a wide range of hardwares. And more importantly, we support different kind of fine-tuning recipes, not only the SFT, RL, we also support OPD, on-policy distillation. And we have verified the mouse framework with over 1,000 GPUs for RL training workload, and we accelerate the RL training throughput. Like for example, for Kimi K2.6, we can speed up the generation throughput to 12.5K output tokens per minute per GPU. And we also have optimized the stability, such as the R3 TITO, as we mentioned, and the precision aligned training, which help us to decrease the training inference mismatch. And we also support the fault tolerance recovery. And we support different kind of system, like the cluster backends, such as Rayon, Kubernetes, Slurm, and bare metal, etc. And finally, I'd like to mention some of our recent releases, like day zero support for Kimi K3, which is nearly a 3 trillion parameters model, and we do the fine-tuning with mouse on like different kind of tasks, such as the AMI mass problem. So we, through the RL fine-tuning, we can increase the accuracy from 40-ish to 76%. And for the Inkling model from Thinking Machines Lab, which is also a 1 trillion level parameter model, we do the full parameter fine-tuning and the LoRa fine-tuning, and we also optimize the LoRa adapter synchronization, which means merge the LoRa rank into the SGLang inference engine. So this kind of things, we optimize it from almost 50 seconds to less than 3 seconds. And finally, we have a recent blog post about mixed precision training, as we mentioned before. So we verified that with different kind of precision choices such as MX FF8 or NVFP4, we can maintain the model's accuracy and stability during RL training, and we can also fundamentally and accelerate the raw speed and training speed by a great margin. Yeah, I think that's all about today's presentation. Thank you very much for the patience.
Thank you, Sheng. All right, our final speaker is Romain Bardouage from, he's a co-founder of SkyPilot. So Romain will make the case that AI needs an open compute layer. Please welcome Romain to the stage.
All right, there you go. Cool, thanks everyone. I'm Romil, one of the co-founders of the SkyPilot project. And today, we heard really good talks about open environments, how to do RL in an open manner. I want to make the case that there's a need for an open compute layer for AI, and specifically something that sits between your workloads and the actual GPUs where your workloads run. So building AI infra is really hard, right? And let me walk you through it from OpenAI's perspective. Back in 2016, they signed an exclusive agreement with Azure to have Azure as the exclusive provider for the GPUs. But in 2024, they signed yet another deal with Oracle for $10 billion to get more compute. And only just a year later, they signed another $11 billion deal with CoreWeave to get even more GPUs, right? And even that's not enough. Like, you can see Sam Altman tweeting about, like, hey, we need more and more GPUs. Just give us a call if you can, like, secure more GPUs for us. So if the most capitalized company on the planet right now cannot secure enough GPUs, and if they're not able to get it in a single cluster, there's a good chance you also probably cannot do that right now. And so this GPU crunch is very, very real. And if you look at the typical AI organization today, typically you have an AI team, which has, say, some neo-cloud reservation. Maybe they signed like a 2-year or 3-year deal with one of the neo-clouds when hyperscalers didn't have capacity. Then they added some on-demand instances, maybe from the hyperscalers, just to supplement that capacity. But then they also end up having some kind of on-prem clusters, maybe for regulatory reasons, or they just want to keep data on-prem. And then you have customers in Europe, so you need to spin up clusters in Europe as well, so you need to maintain another cluster there. And then finally, you need a ton of CPUs to run your environments and sandboxes, and for that, you need to maintain another CPU cluster. So each of these is sort of a decision made at a point in time where it made sense to do that, but now you end up with this like big collection of clusters that you're now responsible for managing, right? And in some sense, reinforcement learning makes it worse, right? It makes it from, it makes it a scheduling problem, because if you think about reinforcement learning today, this whole thing is one job, but you can see it's composed of many subcomponents. So for example, you can see the trainer itself needs a lot of VRAM, needs many beefy GPUs, but at the same time, the rollout server, the one which is actually generating the trajectories, doesn't need as much VRAM, but needs a ton of them so that it can generate lots of trajectories. And then finally, to actually execute, for example, if you're doing like code generation models, your sandboxes need like a ton of CPUs in parallel to run all the trajectories, and you also need very fast cold starts on them. So the question then becomes like, why not just use existing solutions, right? Like cluster management has been, we've been doing it for a long time, so why not just use Slurm or Kubernetes, right? Slurm is pretty good. I mean, built 2 decades ago from the HPC world, and really, built for advanced scheduling capabilities, one of the best, I would say, quota and priority management systems out there. But it really doesn't support isolation in the form of containers. Yes, you can bolt on like Pyroot and more container layers on top of Slurm, but it wasn't really designed for it. And it wasn't really ever built for serving, so it was more for like batch jobs. Kubernetes, on the other hand, came on the scene about 10 years ago, really popular for microservices, And it's very, very elastic and sort of built for the cloud in some ways, but has like a super steep learning curve. Like if you hand Kubernetes to a researcher, they'll be like, how do I work with this? They'll just probably just have to go to their agent to make it work. And it also doesn't have a lot of primitives that are needed for AI, specifically around like gang scheduling. Again, those are bolt on through like schedulers like Volcano and so on. But it's really hard to make Kubernetes work for AI. But more importantly, both are like single cluster matches. So they still don't solve the problem of like, hey, I have like 10 different clusters running. How do I manage them, right? So what's really missing is not a better scheduler, but something to manage all these different schedulers and platforms that you have today, right? So the goal is not to replace Kubernetes or Slurm. They're really good at what they do. But rather, you want to bridge this gap where you have some workloads like training, serving, sandboxes that you want to run on your compute, which is fragmented across like Kubernetes, Slurm, and so on. And so the idea is if we can have an open, unified compute layer, right, which can optimize availability, figure out what's the best place to run your jobs, handle their execution, and so on, and do this in a way where your workloads don't need to sort of know what's under the hood, that would add like a lot of value to the ecosystem. And that's exactly what we've been building at SkyPilot. It's a completely open source platform to use AI compute wherever you have it. And the idea is you bring your own framework, right? So you bring Ray, PyTorch, OpenEnv, Unsloth, your own frameworks, right? And then you submit them to SkyPilot saying that, hey, I need 8 B300s, for example, to run this job. And then SkyPilot takes care of the orchestration, right? It looks at your compute, your Slurm clusters, Kubernetes clusters, even cloud VMs, and then takes care of like orchestrating those resources, running the jobs, getting you the logs, results, et cetera. And SkyPilot started a few buildings away from here in the Soda Hall here at Berkeley. Open source, pretty active and healthy community of people using it and contributing to it. Also used by some of the biggest companies out there right now. And also, it's kind of rooted in the research we did back in the Sky Computing Lab. So just a really quick walkthrough of like what exactly is SkyPilot, how does it work? It's super simple. The simplest way to get some resources in SkyPilot is just to say, hey, Sky launch, provide what infra you want to run it on, and then state what GPUs you need. If I need to switch over from, say, Kubernetes to AWS, it's just like changing one flag. Similarly, for GPUs, again, your application needs to be aware of what's running under the hood, but you can easily switch what GPU type is provisioned for you by just changing one flag. And then if you want to do more complex stuff, right, like not just provision some GPUs, but actually have a complex job, like a reinforcement learning run, we have this abstraction called job groups, where it's a declarative spec. So you say that, hey, I have a rollout server which needs these resources, needs to run these commands. Then I have to spin up, say, 1,000 sandboxes to run the stuff. I also need to, for example, have the rollout server running on H100s compared to the trainer, which may be running on B200s. And then it just passes over to SkyPilot, and then SkyPilot takes care of like the orchestration of this entire workload for you. And in doing so, it also provides some niceties. Like, for example, it'll provide you service discovery, lifecycle management. If one of the jobs fails, it doesn't mean the entire run needs to fail. It'll just like restart that job for you. Cool. So we've been talking about training, but serving is equally important. And serving also benefits from having a unified platform like this. Specifically, you gain capacity across all your clusters. So instead of having to launch, say, one K-serve instance in one cluster, you can have SkyPilot running inference across all your clusters. And when a failure happens, right, like SkyPilot can seamlessly move over your replicas to a region where you still have capacity. And one of the other benefits of sort of like having all your workloads run through one layer is that you can actually do very interesting stuff by running both inference and training together on the same compute, right? So the idea is you use the same GPUs, same giant cluster to run your jobs. But for example, if the inference request starts spiking up, SkyPilot can dynamically reallocate your resources from training to inference. So it preempts the training jobs. Your checkpointing logic takes care you don't lose data. And then when the inference spike dies out, it will automatically scale down inference again and then continue training. Cool. And I just want to reemphasize all of this is BYOC, right? So it's not like SkyPilot gets you, or like you don't give your credit card to SkyPilot to sort of like buy compute. You bring your own compute from your cloud provider, your own data, everything runs on your own premises. So, I'll end here, but like really quickly, the idea is we don't need to reinvent, or like we don't need to replace Kubernetes or Slurm. They're really good at what they do. What we really need is a unified layer, which sort of like allows you to bridge the gap between your workloads and all those clusters that you're running. Cool. With that, I'll stop here. Thank you so much.